Well, hello everyone. Good afternoon, good morning, good evening, depending on whichever part of the world you're watching us from. I'm Mudit, and with me I have Supreet. Hi, Supreet.
Hey Madit.
So I think most of the folks know Supreet very well by now. She is one of our very strong partners at AI Planet. So she's the founder of Databuzz, and she's also working with JP Morgan, I believe. I'm so sorry.
Morgan Stanley. It's okay.
Okay. Well, you're speaking that I got confused. I'm like, shit, sorry, which bank was it?
No.
Yeah, okay. Interesting. So she's with Morgan Stanley. She's a data science leader there. She works as an AVP at Morgan Stanley. And okay, perfect. Great. I'm getting these details correct. And she's also the founder of Databuzz. This is something that I know pretty well. So Databuzz, I think I can introduce, but it will be great if Supreet, maybe you can give some context about what it is.
Yeah, sure. So, Databuzz is very similar to AI Planet. I think all the goal of any of these organizations is they're completely volunteer driven and they are to provide the free resources so that anyone who wants to pivot in this field, learn more about data science, the new trends in AI, they can rely on our LinkedIn pages, on our websites for further resources. And such sessions, which are AI driven and we talk about an AI topic, are one of the ways to provide you with that knowledge. So that is the goal of Databuzz, very similar to AI Planet. And if you haven't checked out, you can check out our LinkedIn page. And I try to post something at least once every week of whatever is happening. These days it's Chat GPT. So yeah, check it out.
Yeah.
Thanks, Madhu.
Thanks to you for that introduction. And since you mentioned similar to AI Planet, let me give a brief introduction of AI Planet in case anyone is new. I see a hi from Kushal on the chat. So, hi, Kushal. Glad to have you here. To briefly introduce AI Planet, we are a global community of data science. Our vision is to educate and build AI for everyone to solve some of the meaningful problems out there. So, if you log on to aiplanet.com, you can see a ton of resources which are created by folks like Supreet, like Aditya, who come forward and contribute for the community. Our community is 300K plus strong right now, and apart from that, we have recently released an AI marketplace, which is an avenue where you can find pre-trained models via secured and scalable APIs. That's a brief introduction of AI Planet, and without any further ado, let us dive into the session. So this session will be led by Aditya, who is an explainable AI researcher at KULUM. He has been in the industry for 7 years. If you have been in the community of AI Planet for a while, you might have seen him before, or you might have read his works, or his book maybe, on various things. He is a very proactive contributor to the AI ecosystem. He's also worked with various companies like West Pharma, Microsoft, Intel, and all. And with this, let me quickly probably loop him in. And this session is around TCAV with Explainable AI, which is a Google AI framework. Okay, so it's around Explainable AI, as you can understand with the name of the session. But yeah, I think he's the best person to introduce it further. So let's loop him in, Supreet. Yeah.
Yes, let's look
Okay.
them in. Let
Okay,
me
Okay.
thanks,
open.
Udit. Thanks, Suprit. So, welcome again, everyone, to this session on explainable AI with TCAV. So, TCAV is actually a nice framework from Google AI, and we are going to discuss more about it in this session. So, this was about me, but I think Mudit has already introduced myself, so I won't spend much time on it. I'll quickly jump into the topics that we want to discuss for today. So, first of all, we are going to start by discussing about TCAV, like what exactly it is. And I'll try to give you a very intuitive understanding of TCAV. Now, the concepts of TCAV and how it works can be complicated, but so that like I want to explain in very simple words so that everyone can understand. So I want to give this intuitive understanding of TCAV first. And more importantly, whenever we talk about explainable AI frameworks, I think most of you had heard about like something like SHAP or something like Lime, which are one of the most popular, like explainable AI frameworks which is there or which is widely used. But when we talk about explainable AI, there are various other things which are also associated. And sometimes popular frameworks such as Lime and SHAP are not very powerful enough to bring those other aspects of explainability. And that is where we are going to spend some time to understand the difference between TCAV and what are the key components which TCAV brings in, which is quite different from other explainable AI frameworks. And finally, I think the most interesting part of the session will be towards the end, when we are going to discuss about potential application using something like TCAV, which presents a concept-based explanation. So we are going to again understand and discuss what exactly is this concept-based explanation and what kind of potential applications can be there considering the concept-based explanations which are provided through TCAV. So without any further delay, we would jump right into the topic about understanding TCAV intuitively. Now, before we even start getting into the topic, we want to still understand the key needs of explainable AI if you're very new to this particular topic. So I'll give you a quick recap of that. Now, when we talk about machine learning in general, machine learning needs some kind of training data to create a model, and using some new data we get certain predictions. So the main goal of machine learning algorithm is nothing but to map the given input and the initial set of output that you give, and it forms a model around it, and based on that certain predictions which are generated. And when machine learning was not there, most of these models or whatever the predictions or the results that we used to get was through some kind of user defined or some kind of domain expert defined rule, which is usually done by the programmer or the person who makes the software program, and based on that we get the specific output. But with machine learning, these rules or the patterns which kind of connects the input and output are kind of learned automatically, and we get the required predicted result. But the problem is, like as we see in most application domains, especially something like somewhere where we have high critical domains, such as maybe healthcare, or maybe to some extent in finance or banking, or even in security related domain, these machine learning models are considered completely as black boxes. So when these machine learning models give some kind of output or some kind of predictions, it is not very clear why we get that specific output or why we get that specific prediction. And that is where explainable AI comes in. Explainable AI tries to give justification to the different model predictions that we get. Okay, so with explainable AI, we can make our black box model more understandable, more interpretable, so that the consumers of AI models can actually understand the working behind it. And with this, the transparency of AI model or machine learning models are further increased, and hence it kind of promotes adoption of AI or machine learning models. So that is the need for explainable AI. But when we talk about explainable AI or the concept of dimensionality in general, as I always tell, that explainability is a multi-dimensional concept. It is not about getting some kind of explanation from one particular angle, but there are different dimensions which are involved in it. So we can, on a very broad level, we can actually categorize the different dimensions of explainability into these four segments. We can provide explainability in terms of the data which is used for preparing the machine learning models. This includes generating some kind of insights or information about the data, maybe even, let's say, finding out whether the data set is biased or not, so that there is a potential of getting a biased prediction. And there can be, again, like further work which can be done towards understanding the overall distribution of the data, some kind of issues or some kind of, let's say, problem or gap which is there with the data, and generating some insights around the data. Now, the most important dimension that we have seen so far is around the model. And most of the popular explainable AI methods, such as LIME, SHAP, these are all model-centric methods. Like basically, it tries to give you insights about the machine learning model and the features which are considered important by the machine learning model. So these are mostly model-based methods or model-centric methods, which tries to explain let's say, about the weights and biases which are involved in the model, or maybe the parameters or typical hyperparameters which are involved in the model towards making a certain prediction. Now, another dimension of explainability is based on the outcome. For example, in certain cases, you might have seen that along with a predicted result, you might also get some kind of a confidence interval, that this is the uppermost band of the prediction, or maybe this is the lowermost band, and anything which is predicted out of the model is expected to be within this range. So we always try to kind of relate the output with maybe some kind of historical value, and we say that it should be within this particular range. In some other cases, there is another type of explainable AI method, which is called as counterfactual explanation, which also tells you the minimum changes which are required in the features which are involved towards making the prediction to get a separate prediction, or maybe to get a different prediction. So these kind of explanations are actually surrounds the outcome, the predicted outcome of the model, and it gives you insights about the outcome related dimension of explainability. And another, or maybe the last but not the least dimension of explainability that we have is related to the end user or the consumers of AI model. So typically, nowadays, as we see that the adoption of AI is increasing significantly, there can be non-technical, consumers of AI as well, who doesn't have necessary understanding of how machine learning models work, but still they use machine learning models for their day-to-day life. So for them, it is also important to create the right level of abstraction, so that right amount of details are included towards creating the explanation. So if we give something which is complicated for them to understand, it is very difficult and they might not find it human friendly. So the end user aspect or the end user dimension of explainability kind of ensures that whatever explainability that we provide is actually human friendly. Okay, so in short, there are different dimensions of explainability, and it is not possible for one explainable AI method to actually cover all the 4 different dimensions of explainability. Most of the XAI methods are model centric, but definitely I named a couple of them which tries to cover the other dimensions of explainability as well. But coming to today's topic of discussion regarding TCAV, TCAV is something which is more closely related to the end user aspect of explainability. It tries to explain or give explanation in certain simple concepts which end user or non-technical end users can actually understand. But so what exactly is TCAV? So TCAV stands for testing with concept activation vectors. Okay. So concept activation vectors is a kind of technique which is used to generate some kind of concept importance from the given data and the model. So TCAV is an XAI method which was actually developed by Google AI, and it can be applied with even complicated deep neural network model and even with unstructured data. Unlike some of the XAI methods, which is actually applicable with structured data sets, but TCAV can be applied with unstructured data. Now, the main important thing of TCAV is it gives explanations in terms of higher level abstract concepts, such as, let's say, the color of a particular object, maybe the shape of a particular object, or if there are, let's say, humans involved. Even explanation can be given in terms of the gender, the race, or any other, let's say, high level abstract concept. And this is very similar to how even humans communicate. Okay. For example, if I ask someone to kind of describe how a doctor looks like, in most cases, people will say a doctor, is someone who wears a white lab coat and might have something like a stethoscope around his neck. But in some cases, if we even ask, TCAV to describe the same thing from maybe images of doctor, there are other aspects of the explainability that can also be generated. For example, if you see this image here, you also see along with the concept importance of white coat and stethoscope, there is a good amount of concept importance which is given for the concept of male. So this highlights that it is possible that the data set is actually biased, and the image data set that was used towards training this model might contain more images from let's say male class instead of the female class, and that's why the concept importance of this abstract high level class of male in this case is much high. So this indicates that there is a presence of biased data set. So using TCAV, there are other benefits that we get. But most importantly, the concepts or the classes which are used to give these explanations might not be even part of the training input. But if you consider the same thing with other XAI methods such as LIME and SHAP, it tries to explain or give, let's say, information about important features considered by the model, but most of the features are actually part of the data set. Now, if you want to include some new feature, or maybe if you want to add a new concept for giving the explainability, it is not possible. You need to either retrain the model, consider the, let's say, the new concept as a new feature and retrain the model to get the explanation, or you won't be able to give the explanation in other concepts which is not part of the data set. But if you consider TCAV, it can actually give explanation in terms of concepts which are even not part of the data set, and it can automatically learn these concepts from the data. So TCAV kind of is based on something called as concept activation vectors, which is, I would say, the key component of TCAV. And this concept activation vector, what it tries to do is, from a set of human defined or from a set of user defined concept, it tries to generate a vector, a numerical vector, which is like a mapping of the concept with respect to the data set that we have and with respect to the training model or the trained model that we have. So using TCAV, it tries to apply this concept activation vector, and it tries to use something called as directional derivatives, which is basically it's like quantifying the importance of the concept. Okay, so from a very high level, when we try to use TCAV, we try to give some kind of user-defined concept, and based on that, it internally generates certain concept activation vectors, and using that, we can actually quantify that. What is the importance of the your concept activation vector towards making the certain prediction? Okay, so we generate some kind of score, and finally we can even validate. It doesn't, like TCAV doesn't just stop based on one sample of the data. It goes through the entire data set. It goes through different smaller chunks of the data and then tries to calculate the concept importance. Okay, and as I mentioned, that in order to learn, new concept, you do not need, to retrain the data. It can automatically learn from some examples the importance of a particular concept, and then it tells you that, okay, for this sample of the data, the importance of this concept is not there. Okay, so it can easily learn a particular concept from a few examples of the data. Okay, and when we talk about TCAV again, the goal is to understand how important a particular concept is for making a certain prediction. Okay, so the goals of TCAV can actually be, further classified into these four goals. The developers of TCAV had a good planning when they made this particular framework. So they had clearly defined these four goals, which TCAV is supposed to meet. One of the goals is accessibility. It ensures that, anyone who doesn't have the necessary knowledge of machine learning can also use it. They can define their own concept, and with their concepts defined, it can actually be applied with TCAV to generate the required explanation. It can also be used for customizing. Like, let's say if I want to add a new concept after a certain point of time, that is also possible. So without making any changes to the data, without making any changes to the model, that is also further possible. It provides plugin readiness. So as I mentioned, that you don't need to fine tune anything, fine tune the machine learning models or maybe make changes to the data. You can use whatever you have and apply that to get the results. And most importantly, it provides global interpretability. So global interpretability means, like, whenever we are trying to apply any kind of explanation methods, either we can generate explanation for a single instance of data, just to understand that why we are getting an output for a single sample of the data, or we can also understand that why a certain class or why a certain set of data is being predicted to a particular class. So that is about global interpretability, which tries to give explanation about the entire, let's say, data set, or maybe multiple samples of the data set together. So TCAV is actually designed to give global interpretability and not just local interpretability, which is for one single data instance. So we have briefly discussed already about the approach of TCAV, but just to consider this as a step-by-step approach, the very first thing that we do is define the concept of interest. For example, let's say if we want to make an image classifier which tries to classify between let's say zebra and other animal, then we can define a concept like black stripes. Okay, and then we can try to find out how important is the presence of black stripe while predicting the particular animal as zebra. So black stripe can be one of the concepts that can be considered. So we can do one thing, like basically from the data set that we have, we can either gather some small sample of data set which gives you the information about the black stripes, and use that sample to prepare our concepts of interest. And likewise, along with, let's say, black stripe, if we want some other type of concept, let's say, I don't know, maybe something like a hexagonal pattern, or maybe some other color, and maybe some other texture if we want to introduce. So these can actually be considered as different concepts or concept of interest. Now, using these concept of interest, the second most important step comes in, which is actually done by the algorithm, which tries to learn these concept activation vectors. So the algorithm tries to apply the concepts that we feed in, and using the using a linear classifier, tries to differentiate between the activations of the different concepts generated, which means that it tries to check how much is like a certain data instance is getting activated based on the concept that we feed in, and based on that it calculates or it creates a new concept activation vector for each of the concept that we generate. The second part, the third step after this comes towards estimating the directional derivative. Direction derivatives are used to quantify the sensitivity of a particular model prediction towards the concept. This is similar to sensitivity analysis, which is also often done for creating explainability from the output, where we try to change the feature and we try to then observe how much change that we get in the output. Like for example, if I change the increase the feature value of a particular feature, if it is completely changing the output, then we can kind of get an inference that the particular model is very much sensitive to a specific feature. Okay. So using directivity or directional derivatives, we can actually understand or quantify the sensitivity of a model prediction towards a particular concept. And this directional derivative is actually used to measure the importance of a particular concept. So in our, let's say, zebra classifier, we can use this directional derivative to actually measure the importance of black stripes, which are used for predicting zebras. So based on that, we can create TCAV scores. Like basically it will create a certain measure or a certain score for each of the the concept of interest that we have. And from there, from the score, we can actually get an understanding that how much importance do we get or do we give to a particular concept for predicting a certain class. And finally, a TCAV or this concept activation vector is validated in multiple fold. It is not just, let's say, these concept activation vectors are created on one sample of the data, but rather instead of a single batch of data, the concepts, the concept importance or the concept importance score is generated on different batches of data. So with that, whatever the importance score that we get is much more generalized. And from there, we can say that it provides global explainability, which is actually applicable to the entire class and not just a single, let's say, a sample or a single batch of data. Now let's try to understand the difference between TCAV and other XAI framework. So as I was mentioning that TCAV is quite different from other popular XAI frameworks such as Lime and SHAP. And more importantly, if you have applied line before, you might have also noticed this, that line can sometimes generate very contradicting explanation, which means that for a certain data instance, it might tell you that one particular feature is more important towards, let's say, one of the particular class than the other feature. But then again, if you change the data instance, if you try with a different example, then it will tell you that maybe the other feature is more important than the previous feature. So sometimes the explanation provided by the line framework can be very contradicting, and it's confusing to especially like to someone who doesn't have any deep technical knowledge of machine learning. So from the local explanations which are given by line, it is hard to generalize and hard to understand a global view of the entire explanation. So with like in this particular situation, line is not very trustworthy. It is very difficult to trust the explanations which are generated by the line framework. Rather, if you consider TCAV, TCAV actually generates explanations which are not just true for one single data instance, but it is true for the entire class or the entire category of data that we have. So I think this is a very major, I mean, it's a major advantage of TCAV over line, which actually helps to increase the user's trust. The user can actually understand that why a certain set of data is being predicted towards a certain category or towards a certain class. So based on the concept importance, you can get this explanation very clearly. It gives you the importance of a certain concept which holds true for the entire set of data and not just one single sample. Now, concept-based explanations are also very close to how humans would try to explain based on certain abstract concepts which are very easy to understand. But if you think about it, the explanations which are provided by line and SHAP, these are feature-based explanations which are very model-centric. Now, sometimes in order to understand the feature, you might also need to have kind of a domain knowledge on that particular topic. For example, let's say if you have a machine learning model which can tell you whether a person has diabetes or not, and one of the feature that you're using is something like, let's say, diabetes pedigree function, which is a kind of measure which tells you the extent of, like how much prone you are to diabetes. But this feature does require a kind of domain knowledge to understand it properly. So it is quite difficult for non-expert users who doesn't necessarily have any technical knowledge of machine learning, or maybe they even lack the domain knowledge on that particular topic. Whereas TCAV generates these explanation in terms of abstract concept. So it can be easily personalized as well. You do not need to have deep technical knowledge or maybe even domain knowledge on that topic to create the explanations. You can give your own concepts which can be abstract, which can be high level, but at the same time it's human friendly, and using those concepts the explanations can be generated. So TCAV actually generates explanations which are much more human friendly. And as we were discussing, that feature-based explanations such as maybe Lime, SHAP or others, which gives you the importance of a certain feature, depends on the features which are used in the particular data set, which are used by the, let's say, by the model. Now, if you want to include new feature, you need to retrain the model, or you are just limited to the features which are used during the model. So that's why introducing a new concept which is not part of the model is very difficult using those methods. And this is a benefit, or this is an advantage that we get using the TCAV framework. We can introduce new feature. We can even, let's say, add new concepts if we want. And we don't need to retrain the model. We can introduce concepts which are not part of the model, and giving some example, it can automatically learn or distinguish between the presence of that particular concept in the data instance and with the absence of the concept from the instance. And model explainability is not just the only benefit that we get from TCAV. As I was mentioning in the initial example of, let's say, identifying doctors from images, you can also understand if the data set that is used for training the model is balanced or not, or whether there is a possibility or presence of some kind of bias in the data set. So using TCAV, we can consider, that like we can obtain the concept importance, which can actually be considered as a metric to compare between different models. And using this metric, we can also get an understanding that how much bias is actually present in the model or even in the data set. So explainability is definitely one of the key things that we get from TCAV, but it is not the only thing. We can easily identify how much fair the machine learning model is, or whether there is some kind of bias in the data set. But unfortunately, TCAV also has some limitation, some drawback. So let us also discuss the drawbacks or the limitations of TCAV. So currently, TCAV is actually limited to just neural network. And more specifically, TCAV does have some challenges with shallow network, which basically has just two layers. So TCAV is more suited for deep neural network, which actually has multiple layers, and you have the, let's say, the information propagated throughout the different layers of the deep neural network. So TCAV is more effective. And I would say that is one of the major reasons because of which the adoption of TCAV is slightly lesser as compared to Lime and SHAP, as Lime and SHAP can actually be applied for classical machine learning algorithms, and it can be very easily applied. But TCAV has this limitation. Another drawback of TCAV is that it is very highly prone to data drift. Now, if you are unaware of what data drift is, typically when we train a machine learning model, we expect the training data to have the same statistical properties as the test or the inference data. If, let's say, some of the statistical properties of the training data and the inference data, if it is not same, then we say that there is some kind of drift which is present. And this data drift is one of the reasons why, let's say, machine learning models might not have the same performance in the inference phase as compared to the training phase. Okay, so there can be a lot of data quality issues also present, which can bring data drift or other such problem. And you have something called as adversarial effect, which means that it is kind of injecting some kind of noise in your, let's say, data set or in your machine learning model, because of which the machine learning model might not perform as expected. So TCAV is actually highly prone towards such problems such as data drift, adversarial effect, or any other data quality issue. So if you're using TCAV, it is better to ensure that the training data and the inference data, or even if you have concepts which are provided as images, they actually have the have similar statistical properties. So if the statistical properties are not same, then the concepts generated can become affected due to the noise or the data impurity issues, which means that the concept importance or the concept scores that will be generated, it will not be very stable. So this is a limitation of the TCAV model. And when we use TCAV, especially with image model, we might also need to prepare the images from which the concepts will be learned. So sometimes creating these concept data set can also be challenging, and it can be an expensive task depending upon the specific use case. So although you do not need any machine learning knowledge to prepare a concept data set, but still it is expected that there is some kind of common end user knowledge is required to create the concept image, and it can be time consuming as well. Like, as you know, that creating annotated data set can be sometimes really challenging, and it can have its own set of challenges. So creating this customized user defined concept data set for using in TCAV can sometimes be very difficult. So these are some of the prominent limitations of the TCAV algorithm. But now coming to, I think, the best part of this session is learning about the different potential applications of TCAV, or which kind of gives you the concept-based explanation. So first of all, we already discussed about this, that using TCAV, you can estimate transparency and fairness in AI or machine learning model. Like from TCAV, you can actually have certain concepts which are, let's say, which kind of represents the demographic information of the data set. And from there, if you see that there is a high concept importance which is given to any of those demographic information or the demographic concept, you can get an understanding that there is some kind of bias towards that specific demographic segment. So detecting bias can actually be easily done using TCAV, and using the scores which are generated, the concept importance scores which are generated from TCAV. You can use that as a measure for transparency or fairness in AI model. So this is a very interesting application of TCAV, and definitely it allows you to use TCAV other than for getting the explainability part. And then I was mentioning about adversarial effect and how TCAV is actually prone towards adversarial effect. Now, it's true that it is a limitation of TCAV as such, but if you think in another way, you can actually detect adverse effect using TCAV, or maybe using concept activation vector. So using TCAV, you can create TCAV scores with your data set, and the scores will be an indication that whether you have some kind of issue with your data set or not, or some kind of adversarial effect with your data set or not. So if an image gets impacted by any kind of adversarial effect, the concept importance would also change. So TCAV can actually help you to detect adversarial attacks on images. So with adversarial attacks, as I was mentioning, that if you have an
Aditya, hi. I think, sorry to interrupt. I think you went on mute or your mic is disconnected. Do please check.
Am I audible now?
Yeah, you're audible now. Yeah.
Okay, sorry. Till last, which point did you hear clearly?
Yeah, I think concept based image clustering should be fine. Yeah, we could
It's
hear
fine.
this part. Yeah. Yeah.
Okay, perfect. All right. Yeah, so as I was telling, that concept-based image clustering is another interesting application of TCAV. So you might have heard about, let's say, something like visual image search, especially I think like in Google Chrome, or maybe even in Bing, you have the option of searching images based on another images, right? So basically, we do a visual search, and in visual search, the way we do it is we kind of feed an image segment, and we say that we want certain images which are similar to a particular sample. So it's a deep learning based image search, which is usually done in such cases. But in this case, you can actually do clustering based on the concepts that we create. So these concepts, it's like let's say from the concept images that we share. So from the concept images, we can actually search other set of data based on the concepts that we define. Okay, so it's like concept based image clustering, and there have been some work which is actually done around this area, so I would strongly recommend all of you to go through it. But there is kind of a stronger possibility of adopting TCAV for creating better concept based image clustering techniques. Then, one of the limitations of TCAV, as I was mentioning, was towards creating kind of a labeled or an annotated data set for creating the concept. But the problem is, you need to still invest some time to create the annotated data set. So it can be a challenge. So there have been some work which has been proposed towards creating automated concept-based explanation, which is like when you feed a particular image, the entire image can be broken down into smaller segments, and each of the smaller segments can actually be considered as a concept sample. And then you can say that presence of a certain type of maybe car, I mean a tire, for understanding whether that is a particular car or not, or maybe some other visual features which can actually be used as a concept. So we have something called as automated concept based explanation, which can be used for creating or for generating these concepts automatically. And there can be many such applications around it. So then we have another interesting application, which is around concept-based counterfactual explanation. Now, initially when I was mentioning that counterfactual explanations are certain explanations which tells you the minimum changes in the feature values which are required to flip the output or to get a different output. Now, like the same counterfactual explanation can be applied with images as well. So in images, the counterfactual explanations are provided in terms of the pixel values usually, like in visual counterfactual explanation searches. But the same thing can actually be done using different concepts. Okay, so we can have concept-based counterfactual explanation. Let's say if we have an image of a jasmine flower, and then we say that what are the typical concepts that can actually explain the, let's say, the structure or the nature of jasmine flower, then we can use something like white petals or maybe small petals as some of the high level concepts. Now let's say if we have a counterfactual explanation which changes the white petals into maybe something like red petal and the smaller size petals into larger size petal, then using these concepts we can actually get an indication that this might relate to the other class that we have in the data set, which is the rose class in this example. Okay, so it's like using concept as a way to create counterfactual explanation rather than the features. So usually counterfactual explanation are feature based explanation, whereas concept based counterfactual explanation are concept based feature based explanation.
Aditya, sorry, I think you just went on mute again a couple of a minute ago or so.
Okay, I think there is some issue which is happening, like I'm getting muted automatically.
I'm not sure. Yeah.
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 Okay. Yeah. So as I was mentioning that with concept-based counterfactual explanation, the concepts can actually be used instead of the feature value. So in typical counterfactual explanation, it is a feature-based thing. So it kind of tells you the minimum changes which are required in the feature values to get a different output. So instead of feature-based counterfactual, we can also have concept-based counterfactual explanation using TCAV. Okay, so it can, like in let's say another example can be if you are using let's say some kind of image data set to distinguish between maybe clear sky or versus something which kind of tells you rainfall. So with clear sky, we kind of tries to relate that it is sunny day, or maybe with cloudy sky, we can say that it can give indication of rainfall. So with concept-based counterfactual explanation, we can actually alter the concept from clear sky to cloudy sky and maybe use that to tell whether there is a possibility of a sunny day or whether there is possibility of rainfall. Okay, so concept-based counterfactual explanation is another interesting application of TCAV. So that's mostly it. Like we mostly discussed about, firstly, by understanding TCAV intuitively, we also learned about the differences of TCAV with other XAI framework. We have briefly discussed about some of the key advantages and even the limitations of TCAV, which can be there. And finally, we have discussed about some of the potential applications of TCAV or such a concept-based explanation. So there are some interesting hands-on tutorial which is provided in the GitHub repository of my book. Like I've actually written a book on explainable AI, which is called as Applied Machine Learning Explainability Technique, which includes a chapter on TCAP, but at the same time, it also presents you about different XAI method. So if you're interested in XAI, please do take a look at this book and you get a lot of good code tutorials which you can actually try out. And this is openly available. You can go and visit this particular link where you can get the necessary code tutorials on different explainable AI methods, including TCAV. Okay. So thank you for attending the session. And now I do see some set of questions in the chat forum. So let me maybe spend some time to go through these questions.
Great. Thanks, Aditya, for the session.
Thank you, sir.
I think since you mentioned the book, right, I would like to add something to the audience that's listening. I am almost, if you can see my screen, I'm almost done with the book, and it is amazing. So if you are more interested to, whether it will be suited for me, what should be my profession to read this book and all of that, I will be sharing a detailed review of the book. Like, I've scheduled it for 1st March, so you would see that on my LinkedIn if you follow me. So you can also refer to that. So it will be a lot of these concepts that you mentioned, and I see that a lot of these questions are also covered in detail. But we can take 1 or 2 questions here, Aditya, since we have like 10-15 minutes left.
Sure, sure, sure.
Maybe this one. Yeah.
Yes, let's do that.
Okay, could you provide examples of global interpretability and local interpretability? Okay. Uh, Maybe let's take the same diabetes prediction problem as one of the examples. So when I mentioned about local interpretability, it surrounds a single data instance, which means that if you want to find whether a specific person, or let's say if the model has been applied for a specific person and the model predicts the person to have diabetes. So if you want to understand that why the model predicted that the person have diabetes for that specific person, so in such a case, we whatever the explainability that we provide is called as local explainability, which kind of tries to describe for one single instance of data. Now, let's say if you want to get a broader understanding on why, let's say, patients within that particular, let's say, data set has diabetes, or what are the key, features because of which there is a stronger presence of diabetes in certain, people. So in order to get the global understanding, we give global explainability, which is not trying to explain one single instance of the data, but rather the entire data set as a whole. Okay, so it gives you insights about multiple, like chunks of the data, and tells you that because of presence of certain key factors, you can say that a certain person is diabetic. So it will try to highlight that maybe if the, let's say, the blood sugar level of a particular person is beyond a certain value, then in most cases it has been found that the person might have diabetes. So it kind of gives you explainability about the entire class and not just a specific instance. Okay.
Okay. There is another question from Asif himself. Could you explain more about directional derivative?
Okay, so in directional derivative, what happens is whenever we apply these different concepts, like we provide these user-defined concept. For each of the concept, we get a concept activation vector. Now, this concept activation vector, you can consider that similar to a feature engineered value. Like typically with text data, whenever we feed in the raw text value, which is in string format, we might get a numerically encoded vector. If we apply a typical feature engineering technique such as bag of words, or let's say TF-IDF, which kind of creates an encoded feature vector which can be used by the machine learning model. So similarly with TCAV, first we get a concept activation vector, which is more like a numerical representation of the different concepts that we feed in. Now with directional derivative, it is like a mapping technique. It tries to map each of the vector, let's say in a particular horizon, which tells you how much close the specific vectors are for specific samples of the data. Okay, so it's like creating those vector values and maybe plotting them in their own dimensional map, and that is done for all the samples of the data. And then you check that, okay, for one sample, the distance between, let's say, one particular concept activation vector and the image is, let's say, X distance. Now for the other sample, maybe the distance is actually more. Let's say it is twice of the distance in the previous case. So it's 2X, let's say. And similarly, it goes through all the samples and then says that, okay, the distance for, for this particular concept vector on average for all the classes is maybe, let's say, X by 2 for an example. So with that, it kind of estimates how close the concept is towards creating a certain prediction. Okay, so it's like it tries to give you the concept importance based on the proximity of the concept activation vector for a certain class of data or for a certain category of data. Okay.
Okay, thanks. Supreet, you want to pick the next question?
Yeah, I think we can, limitations were already covered, so we can let that be, but we can cover maybe question by Sam. Let's say we have a pre-trained image classification model. How can we use TSAV to explain that?
For a particular image. Okay. First of all, like some examples are included in the code repository that I've shown, where I actually used a pre-trained model. But just to answer your question, the very first thing that we need to give is to feed the concepts. Now, so far, like whatever I have discussed with the with the images and everything, there the concepts are kind of presented as certain textual values. But at the same time, you can also present visual concept. Like let's say if you want to build a tiger classifier, then you actually need some samples of, let's say, the stripes or the colored patches from a tiger image, and use that to create a concept data set. So basically, you need a data set which tells you that samples from this data set would be a particular concept, like it is related to a particular concept. Okay, so that is the second thing that is needed. And then you have your pre-trained model. You can definitely use the pre-trained model, and you have the data set as well. So you feed the pre-trained model as well as the data set in the TCAV algorithm along with the concepts that you have. And then TCAV as an output would tell you the concept importance for each of the user-defined concepts that you have created. Okay, so you can actually get a detailed step-by-step approach in the code tutorial that I have provided, and I think that would be quite helpful. So maybe I'll just go back to the link if you want to take a quick snapshot of it, or maybe I can also share this in chat.
Aditya, you're muted.
Okay. Yeah, I actually just shared the link, I think in private chat. I'm not seeing any option to share that as a comment, but I think you have already done that. Okay.
Yes.
Good. Okay. Okay, great.
Mudit, let's take the next question.
Yeah, sure. So there is one question by Sabyasachi Rath, which is one second. While putting the comments, I lost the window. Supreet, could you please pick that?
Yeah, sure. It's, are there any specific domains where TSAV can be used? Are there any use cases of insurance sector?
Okay, specific domains, I would say TCAV would be really useful, especially for high stake domains where bias in data set can be a problem. Now, coming to your question about insurance sector, I think if you are using something which has problems related to bias in data set, it can be different demographic factors as well. Like even for deciding whether to, maybe deciding the insurance premium or whether to give approval for insurance to a particular, let's say, person. Sometimes the demographic information can create problem. Like it can, misguide machine learning models towards giving a certain prediction which is biased towards a certain demographic segment. So in order to detect those specific scenarios, TCAV would be really useful, would be really helpful.
Okay, thanks. There is one question which I'm not sure if he could answer during this session, but I'll put it across for you to decide. Could you give an example using unstructured healthcare text data?
Okay, so from so far what I have seen, TCAV is mostly useful, especially if you have unstructured data, like images is one case, even with text you can. But the problem is with text data, the volume of the data that you might need is like typically you need more amount of data to generalize that, to learn the concept. Whereas in images, it is actually easier to learn. Now, for the healthcare domain, there actually can be like multiple use cases where let's say different medical records are involved, and from there you want to identify some kind of, let's say, disease name, or maybe some kind of medication names as well. So in such cases, even concepts matter, like especially if you want to relate the diseases to a specific type of symptom. So these symptoms can be the higher level abstract concepts which you can use, and using that you can create an explainability layer, that whenever you, let's say, a patient is kind of said to have a particular disease, why it is said, and you can relate that to certain symptoms which can be used as abstract concepts to get the explainability. But it would be a difficult use case, I would say, especially with text data, as I mentioned, that you actually need a higher volume of data to learn the concepts properly. But it could be very interesting as well. But there is definitely a possibility of of using unstructured data in this healthcare context. Yeah.
Okay. Thanks. Given we have 5 minutes left, we can pick probably one last question, which is this one. Can TCAV be used to cluster images based on multiple concepts at the same time? And how does this affect the clustering results?
Okay, this is also a very interesting question. Like typically clustering, which is done based on, let's say, any kind of visual effect or any kind of visual inspection, which is done. Usually, it is based on a single sample. Even if you see visual search in maybe Bing or even in Google, the visual search is done based on only one sample. But if you think about it, it can definitely be combined, and it might not be an output of one single model, but think of it as, like, let's say, multiple different steps, where from each step you actually provide a particular concept, and based on that you get a certain let's say search result or certain segments which are created. And then if you combine the concepts together, you can actually have a combined class or a combined search result. So it might not be a single step method, but definitely I think it can be done. It can be done separately and then integrated towards getting a final combined set of results.
Okay, great. So yeah, I think with that we are towards the end of the questions and towards the end of the session too. So well, thanks a lot, Aditya, for
Thanks,
taking
man.
this session, answering all the questions, and yeah, and thanks again, Supreet, for partnering with us. A nudge to everyone who's attending: please go and check out the book that Aditya has released on Amazon. We've seen a lot of good reviews, even from Supreet, Chanukya, and many others in the community. So it might be worthwhile to check it out. And yeah,
Yeah, thanks so much, Aditya. The presentation was really nice, visually appealing, and I'm sure everyone enjoyed it as much as we did. Thank you so much.
Thanks, Sophie. Thanks.
thanks everyone. We'll see you all soon. Take care and happy learning.
Yeah.
Bye.
Thank you. Take care,
Bye.
everyone. Bye bye.